Hi students, welcome to my lectures on thermodynamics. In the previous classes, we have discussed about finding out the enthalpy in heating, cooling and during the reaction. In today's class, let us club these three: heating, cooling and reaction that happens in a process. How to take care of all those three things at the same time. Okay, let us go through the example. Consider a reaction that happens. The initial temperature is 300 and final temperature is 800. That means because a process that has happened, that has changed the temperature of the reactants 300 to the products that has temperature has been 800. So between these 2 points, there is some change in enthalpy that has been occurred. Okay, let us take those 2 points. Let us take this as a state 1 and this is a state 2. A process that has happened between state 1 and state 2. Let us mark those points here. Assume this point is the state 1 point, this point is the state 2 point. There is a process that has been happened from state 1 to state 2, because of which there is a change in enthalpy during the process. Our objective is to find out this change in the enthalpy. As you know, sometimes we may not have the information in the actual process. The blue line is the actual process. Sometimes we don't have the sufficient information about the temperature, sufficient information about the pressure. There are many things we may not know the parameters that can able to calculate the change in enthalpy. But we can able to find out the change in the enthalpy in the another route. And if I don't know the parameters in these two, between state 1 and state 2, I can able to go an alternative route. That means instead of going from here to here directly, I can take a path from 1, that is 300 degrees centigrade. I will cool down to 25, conduct a reaction at 25 and heat to the again 300. Because enthalpy is the state function, whether you follow this route or this route, the change in enthalpy will be the same. Because I am following some alternative route, that means I can able to calculate few things, okay, because of this route rather than this route. So let us go to the alternative route to find out the change in enthalpy of this process. And you can see the reactants are at 300 here. But I have some information about the enthalpy of a reaction at 25. That means let me cool down the reactants from 300 to 25. That is called cooling process. Conduct a reaction at 25, because I know the information at 25 degrees centigrade, because in many of the books the enthalpy of the reaction at 25 degrees centigrade is available. So I conduct the reaction and increase the product temperature from 25 to 800. That means I can able to find out, that means what happened with the enthalpy because of this particular process: cooling, reaction and heating. During cooling, that means you should know only reactants you have to cool down. Conduct a reaction and heat the product. During this step, there are no reactants. If complete reaction has been taken place, then you have to heat only the product. If only 50% reaction has been taken place, in such cases, because you have to increase few of the reactants, which is unreacted, plus products. You have to increase the temperature of both unreacted reactants and the products from 25 to 800 degrees centigrade. So in our example, we are focusing on, let us assume complete reaction has been happened. That means during the cooling step, I have to cool down only the reactants. During the heating step, I have to only heat the products. Okay. And finally, the change in enthalpy in the actual process is nothing but cooling, reaction and heating. That is what this particular equation talks about. So that has been mentioned here. So during the cooling step, my initial point is 300, final point is 25. During the heating step, my initial point is 25 and final point is 800. Okay, let us proceed. Let us assume a reaction that has been happened. 1 mole of CO plus 2 moles of hydrogen is giving 1 mole of CH3OH. If this is the reaction happening in this reactor, let us find out the change in enthalpy of the process. The first thing is, before the reaction, what are the things that are present? According to this reaction, let us take initially as per the stoichiometry, 1 mole of monoxide is there and 2 moles of hydrogen is there. So in the reactant side, I will consider only 1 mole of carbon monoxide and 2 mole of hydrogen. And if there are inerts are present, then you have to consider plus number of moles of inerts before the reaction. So let us take the first step, which is cooling step. The cooling step is nothing but cooling of what? Cooling of the reactants. There are 2 reactants here. One is monoxide and second is hydrogen. So the first term is for the monoxide and second term is for the hydrogen. MCP/dT, integral MCP/dT is nothing but your enthalpy of the cooling or heating. So because it's a cooling, NC integral, what is the starting point? The starting point is 300, ending point is 25. That's why integration you have to carry out for the starting point 300, ending point 25 into Cp of carbon monoxide into dt plus number of moles of hydrogen into integral 300 to 25 Cp of hydrogen into dt. So let us multiply and divide it by R. So take one R inside. Okay, in such cases NCO into R integral 300 to 25 Cp of CO by R into dt plus moles of hydrogen into R into integral 300 to 25 Cp of hydrogen into dt. These are the famous. If you remember, these 2 integrations is nothing but ICPH. If you follow my earlier lectures, you will understand what is ICPH. Okay, then this delta H in cooling is nothing but moles of carbon monoxide into R into ICPH of carbon monoxide plus moles of hydrogen into R into ICPH of hydrogen. Okay. So ICPH is nothing but MCPH into temperature difference. NC0 R into MCPH into T2 minus T1. What is T2? What is T1? What is the initial temperature? 300. Final temperature is 25. The T2 minus T1 is nothing but 25 minus 300. Okay, this is 300. Similarly, for the hydrogen, I know using the data in the books, I can calculate the MCPH of carbon monoxide and MCPH of hydrogen. R is 8.314. So if I put everything together into this formula, I can able to get delta H of cooling is minus 27790.58 joules. That means I got the first term. Second term, we have learned many ways. So using enthalpy of formation data, you can calculate what is the enthalpy of the reaction, or heat of combustion data you can use to calculate what is this enthalpy of the reaction. So like that, the enthalpy of this particular reaction, you can able to do some background work. You can able to calculate the enthalpy of the reaction at a 298 or 25 degrees centigrade is minus 90135 joules. That means I got the second term. Third term. What is this third term indicating? Heating step. That means heating the products from 25 to 800 degrees centigrade. So that is right. Moles of CH3OH plus delta H of CH3OH. Heating step. How many moles of CH3OH will be there for the heating? As per this stoichiometry. So 1 mole of CO plus 2 moles of hydrogen react to form 1 mole of CH3OH. So the product moles is also 1. So and into integral 25 to 800, Cp of CH3OH into dt. Okay. Why 25 to 800? Because my starting point is now 25, the ending point is 800. If you, same way, if you multiply and divide it by R, take 1 R inside, you get delta H of the heating is moles of CH3OH R into integral 25 to 800 Cp of CH3OH by R into dt. If you remember this integration term in my previous lectures, it is nothing but ICPH of CH3OH. So the way you can calculate whatever the example I have taught, in the similar way you can calculate what is the ICPH of CH3OH. Once you get what is the ICPH is nothing but MCPH into T2 minus T1. So you can calculate the MCPH. MCPH for CH3OH is 1.955. So once you put up here, you get enthalpy of the heating is 12596.74 joules. Now this enthalpy of the enthalpy of the process is combined with enthalpy of cooling, reaction and heating. You have got all the three terms required to calculate the enthalpy of the process. Okay, that means you add up together. Finally, you get the enthalpy of this particular process is 105,328.84 joules. Okay, I hope now you understood that how to calculate the enthalpy of any process using the combinations of heatings, cooling, heating, reaction and cooling. See, you have to consider the reaction step because there is some reaction that is happening. In other processes, reaction is not necessary. Okay, in such cases only heating and cooling is required. So that is what you are going to learn in the future. And thank you very much for your time, and let us meet with a new lecture. See you.